All right, we are going to look at how to solve difficult, high-degree polynomial equations. Okay, when we want to solve any quadratic equation, we have this tool that works every single time called the quadratic formula, right? But when you start getting into higher degree polynomials, you don't have that, right? In very specific situations, you can have a formula that will get you the solution to this type of equation. But in general, for higher degree polynomial equations, you do not have one technique that's going to solve all the equations for you. So that's what we need to do. The process of solving these higher degree polynomial equations gets more complicated. So I'm going to go over the procedure for how you would go through and solve most of those in general, the ones that we have in this class. You can get into even more complicated situations than we have right here, but I'm going to show you how to do most of the ones that are going to come up in this class. So the first thing that we need to discuss is the rational zero theorem. And what this says, this is convenient, if you have a polynomial, you can narrow down the possible rational zeros of that thing by using this formula down here. Basically what you do is you take the factors of the constant term, so that's your constant, your a sub 0 up here in this formula, whatever your just number is, there's no variable on it, right? Like at the end of your polynomial you have a plus 7, that's your constant, okay? So we look at the factors of the constant and we list them in the numerator of a fraction. Then we look at the factors of the leading coefficient, and we list those in the denominator of that fraction. And then what you do is you look at all possible fractions that you can come up with in that procedure, and those are your possible rational zeros. Okay, they're not all going to be rational zeros, but what this is saying is that if there is a rational zero for this polynomial, it's going to be one of those things in your list. And that's going to be helpful to us because it's going to help us kind of be a little bit more surgical when we go in there and try to find our first factor of these polynomials. There's kind of a few points you can see. There's a few properties coming up here towards the end of this section, and I'm just going to simplify these a little bit for you because basically the takeaway here is that the degree of your polynomial is how many solutions that polynomial has. Right? That's not the whole story here, but that's kind of the big takeaway that we want to leave here with, is that if you have a 5th degree polynomial, it has 5 solutions. If you have a 2nd degree polynomial equation, it has 2 solutions. If you have a 49th degree polynomial equation, it has 49 solutions. Okay? Now you might stop and say, well, wait a minute, I've solved quadratic equations that only had 1 solution, but you're telling me that they should all have 2. And the answer is they did all have 2, right? If you're having that question, it's a reasonable question, but it has to do with multiplicity. If you solved a quadratic equation and just got the 1 solution of 6, then what you really got was 2 solutions and they were both 6, right? So you're talking about a multiplicity of 2. And that really is 2 solutions that just match each other, right? It's the same with like people that are identical twins. You wouldn't say, well, there's only one person because they have the identical genes. No, they're 2 separate individuals. It's the same thing here. You have 2 separate solutions. They just happen to be equal to each other. So yes, every polynomial has the number of solutions the same as the degree of that polynomial, okay? So with all that in mind, like that's helpful because we're about to solve a 3rd degree polynomial. So how many solutions are we looking for? 3. We know that before we even get started. We're looking for 3 solutions. So when you find those 3 solutions, then you know you're done. Okay, so let's take a look at how we would do this because it's you know, this is the kind of thing that makes you appreciate that quadratic formula, which, you know, most students don't love the quadratic formula, but once you reach this point and you see how difficult it gets past that, you're like, oh, that is kind of convenient that I could just pull the quadratic formula out and get my solutions every time. In fact, we will end up using the quadratic formula as part of this solution right here. So let's say we have this, x cubed plus 7x squared plus 11x minus 3 equals 0, and I want to solve that. Okay, so first thing I'm going to do is use that rational root theorem that we just talked about a moment ago. So that was that we were going to take the factors of 3 and put them in the numerator of a fraction, and we were going to take the factors of 1, which is our term here on the x cubed term, so 1, and put those in the denominator. So if we look at the possibilities in the numerator, plus or minus 1, plus or minus 3, and the numbers in the denominator, which is just plus or minus 1, that means that our possible rational zeros here are plus or minus 1, plus or minus 3. So that's good. We've narrowed it down from a whole infinite of everything possible. We've narrowed it down to 4 possible rational numbers that can be zeros of this polynomial. Now what we're going to do is let's look at the graph, right? And some people say, oh, you shouldn't look at the graph, that's cheating. That's kind of how it was 40 years ago when you always had to make your own graph, but now graphs are everywhere. You know, you can pull out your phone out of your pocket and look at a graph, right? So it's kind of silly to pretend like that's not a tool that's available to us. So we're going to look at the graph. So I'm going to go over to my graph and I'm going to look at this thing. So remember that the solutions to the equation, right, those are the zeros, those end up being the x-intercepts on the graph. So I go, okay, well, here's a solution, here's an x-intercept, here's one, and here's one. Well, notice that 2 of our 3 x-intercepts don't happen on nice grid lines where I can identify what they are. Like you might look at this one and go, that looks like it's at about 1/2. No, it's not. So don't try to eyeball it because that's the problem. Okay, but we do look here and go, well, this one looks like it's crossing right at -3. And then we go, wait a minute, -3, that sounds familiar. Wasn't that in our list of possible rational zeros? Yes, it was. Remember, plus or minus 1, plus or minus 3? Oh, it looks like plus or minus 3 might be promising because I'm seeing it here on my graph and it's also on my list. So we suspect we're right, but there's a way that we can prove we're right, that -3 is in fact a zero of this polynomial, and it's by doing the division that we did before. So basically what we're going to do is we're going to come back over here and we're going to think about it for a second and go, okay, if x equals -3 is an x-intercept, how do I write that as a factor to the polynomial? So first we're just confirming that it matches, you know, x equals -3 matches the rational root theorem, so that's good. That gives us the courage to go ahead and try it. Okay, so if you think about it, remember it's always x minus whatever the x-intercept is. So x minus -3 becomes x plus 3. That's how that sign change occurs. Sometimes students get confused about the sign change, but it's because it's x minus whatever the number is, which then becomes an x plus 3. So to confirm our already, you know, we're starting to believe at this point that x equals -3 is an x-intercept, meaning it's also a solution to the equation. We're starting to be more sure about it, but we need to verify. And then also that's going to help us progress throughout the problem. So what we're going to do, the next step, is that we are going to divide the original polynomial that we have from the problem, x cubed plus 7x squared plus 11x minus 3, and we are going to divide that by x plus 3, this new factor that we just came up with. We just got this factor by looking at the graph. Okay, now I'm going to skip this part. I'm going to leave it to you to kind of fill in the details because you've already learned how to divide polynomials. But here's the thing. If we divide x cubed plus 7x squared plus 11x minus 3 by x plus 3, a couple things are going to happen. One, if we get 0 as our remainder, then that means that x plus 3 divides that polynomial evenly. It also means that we were right. It also means that we were right about -3 being an x-intercept here, right? So we're going to go through and do that division. And when you do that, in fact, you do get 0 as your remainder, which is great. That confirms to us that we were right about that initial 0, which is going to end up being a solution to the equation, right? So after you do that division, what you end up with is x squared plus 4x minus 1. And you go, okay, well now we just need to solve that. That's great, it's down to a quadratic. And you go about trying to factor it. That's not going to work. So guess what you're going to do? Quadratic formula. So you apply the quadratic formula to this. And once we apply that quadratic formula, what you end up with is x equals -2 plus or minus the square root of 5, right? So then we, like, are we done? Well, let's see. We started with a cubic. We said that means there should be 3 solutions. We found the first one to be x equals -3, and we got 2 more down here with -2 plus or minus square root of 5. And you can even go back and look. Like, you can kind of ask yourself, well, what would -2 plus the square root of 5 be? Well, square root of 5 is going to be a little bigger than 2, right? Because the square root of 4 is 2, so the square root of 5 is a little bit bigger than 2. So -2 plus or minus square root of 5 should be a little bit bigger than 0. Well, that's what, look, one of our solutions here was a little bit bigger than 0. So go, oh, that seems like maybe I'm going in the right directions. That seems like it, it works out. And of course, you could put -2 plus square root of 5 into a calculator and see exactly what it comes out to, or approximate what it comes out to, and see if that matches your values over here and here. And if they look like they line up, then you're good to go. You just found the 3 solutions to that cubic equation, like we just did. Okay? So that's how you do that kind of problem. So just follow these steps here. You start with the rational root theorem. You make a list of your possible zeros. Then you look at the graph and see if any of your x-intercepts match up with those possible zeros. If so, start dividing those factors out. Right? And you might have to do multiple of them. Depends on the complexity of the problem that you're doing. But divide those factors out the same way we did here. And then once you get down to a quadratic, then it's easy, right? Then everything's easy. You're just going to use the quadratic formula to finish the problem off.